These are the solutions, the solution I should say, for mechanics physics C, the 2006 AP test. This is number 1. We have here a block on a slab. Small block of mass 0.5 kilograms is placed on a long slab of mass 3 kilograms as shown above. Initially the slab is at rest and the block has a speed of 4 meters per second to the right. The coefficient of kinetic friction between the block and the slab is 0.2, and there is no friction between the slab and the horizontal surface on which it moves. So, on the dots below that represent the block and the slab, draw and label vectors to represent the forces acting on each block as the block slides on the slab. So, the block will have force of gravity acting on it, and it's moving this way, so the frictional force will oppose its motion. And, sorry, a bug just landed on my paper. And there's also a normal force counteracting that gravitational force. On the slab, we have a gravitational force, but the gravitational force is actually, there's a gravitational force from this, but there's also the gravity from this, right? Those are both pushing down here. This block feels the weight of this one. So there's a couple ways you can do that. You can make two of them, two arrows coming down together, or you can say that this is the force of gravity, which is mBg plus msg, ha ha ha. And then there's a normal force counteracting that, and equal and opposite that frictional force. If this block, if there's a frictional force from this one and this one, then there's an equal and opposite force. The slab on the block on slab. Okay, at some moment later, before the block reaches the right end of the slab, both the block and the slab attain identical speeds Vf. We want to calculate Vf. Well, there's a lot of ways you can approach this, and if you want to see the different approaches, you can look at the scoring rubric at AP Central for this problem. I think the easiest one is conservation of momentum. So because there are no external forces on the system, right? There's an internal force, but if we treat this whole thing as a system, momentum has to be conserved. So initially, only the first block is moving. So let's see. That means at the start, the momentum of the system is the mass of block B, which is 0.50 kilograms, times its velocity, which is 4 meters per second. And if momentum is conserved, that's got to be the momentum the whole time. Now at some time later, they both have the same velocity, so their combined mass is always 3 kilograms plus the 0.5, so 3.5 kilograms for the whole mass. And so at some point later, they have the same velocity, Vf. So that's a very easy way to get there. Give me a calculator. And let's see what we get. Let me do that. We have 0.5 times, let's see, that's right, 0.5 times 4 divided by 3.5 gives us Vf is equal to 0.57 meters per second. There's a kinematics way to do that problem, and there might even be another way. You'll have to check out their scoring rubric. I think this is the easiest one. I think you'd agree with that. Calculate the distance the slab has traveled at the moment it reaches VF. Well, let's see if we can do that. The only force acting on the slab is this frictional force, correct? And that frictional force is equal to the coefficient of friction times the normal force. So we know the coefficient of friction is 0.2, and the normal force here is the force between these two, so that would be 0.5 times g. So the frictional force looks like that is 0.1 times g, that would be 0.98 newtons. And that is a constant force because it's a constant coefficient of friction. So the work done by friction, oops, sorry, got ahead of myself there. The distance the slab has traveled. So now that we have this, we should be able to do work I think I'm actually, the approach that I'm taking, I think I might do part D first and find the work done, and then go back and find that the distance that it's traveled. Let me think about that for a second. If we have the force that's acting on this, I guess that we could do, that is the force that's acting on the slab. Well, let's try this. Let's try, so force, that's the only force acting on the slab, right? So that's the net force on the slab. So net force, 0.98 newtons, is equal to the mass of the slab, which is 3.0 kilograms, times its acceleration. So the acceleration of the slab is 0.98 divided by 3, which is 0.33 meters per second squared. And we're looking for distance. So here's a kinematics problem. I've got acceleration. I want distance. I know initial velocity was 0. And what else do we know? We know something else. Initial velocity is 0. Acceleration, I'm looking for the distance. Oh yeah, we know the final velocity. It's right there. It's 0.57 meters per second. So that looks like the equation. Let me move on to this paper here. We have a little bit more room. This is part C, continued. So VF squared, using this equation, is equal to initial velocity squared plus 2a times x, or distance, whatever you want to call that. So VF squared is 0.57. That's equal to 0 squared plus 2 times the acceleration times distance. So it looks like the distance would be 0.57 divided by 0.57 squared divided by 0.66. That's 0.49 meters. And the work done by friction on the slab from the beginning of its motion until it reaches V. Well, let's see. The constant force. And I think we already found that force, right? So work equals force times distance. That's actually a pretty easy calculation. Now work is equal to force times distance. It's a constant force. That's why we can use that simple form. Remember, if it's not constant, this is an integral. It's an integral of f as a function of x dx. But here, it's constant, so that's 0.98 newtons times, where did our answer go? 0.49 meters. So what's that, about half? So it's going to be about 0.49, I think. 0.98 times 0.49, 0.48 joules of work. And there's another part. Oh, no, is that it? And I guess that's it.